You don't see as many of them here as you do in Canada. Every community with more than 500 people has an ice rink in Canada. That's why we win the gold medal. Typical ice rink. You're sucking heat out of here, you're dumping it out here, you're adding heat from lighting and whatever else. Building heating system. Very energy intensive buildings. Typical ice rink has to get rid of about 425 to 565,000 BTUs of energy per month, or kBtus per month. Most ice rinks got a cooling tower sitting on and they're just dissipating that energy straight to the atmosphere, just to get rid of it. Looking at this chart, basically in Miami or in Munich or in Helsinki, refrigeration loads are roughly, or the amount of heat that's required. Miami, obviously, you don't need a whole lot except for, there's a surprising amount of hot water used in ice rinks. Typically, use water, it's about 140 or 150 degrees to flood on the ice, simply so it bonds better and to get rid of the oxygen from the water, so it makes harder ice. And then, but the refrigeration loads, heat rejection is going to be similar in most places. Roughly about 2 million kilowatt hours worth of energy per year. And there's been a typical chiller, sometimes they'll put what the equivalent of a desuperator on these chillers. Maybe 10 to 15% of the capacity can be used to heat the mystic hot water for showers or whatever, and maybe melt a bit of snow that they shave off the ice. But generally hasn't been used really very much in the past. And whatever they use it for, they can use it to flood the ice, showers, a lot of showers going on in there, melting snow that they take off of the ice probably once an hour or so. And then under ice heating, if an ice rink is used for 8, 10, 12 months a year, you're going to create permafrost below that ice. And what can happen if you got moisture down there is you're going to get the whole ice surface heaving. Not a good thing. Breaks concrete. We look at a typical, this is a double ice rink. Here's the heating requirements of a typical building like that. Once we add the refrigeration loads, look what happens to the cooling loads and domestic hot water needed to flood the ice with them. They change quite a bit. Ice making is pretty energy intensive. During the day, a typical ice rink, you're looking at during the winter heat rejection, you're typically looking at a lull during the day in most ice rinks as kids are in school, and then a big peak in the evening, a little bit shorter peak during the first thing in the morning when kids are going skating practice, hockey practice, whatever. And then in the summer, they're used a bit differently. It's typically used all day long when kids are at home, but they're not going to school. They're going to hockey schools or whatever. You can reject with a conventional chiller. It's not difficult to reject that heat into a ground loop. You can dump that heat into there and then recover it with other heat pumps in other buildings nearby. Problem is, in a lot of places, you've got so much heat that you simply can't use it all. Even with, I've seen buildings where you've got 100,000 square feet of building you're heating, and we're still overheating the ground loop. Simply got to get rid of it. So if you've got a pool attached to it, that's a good mix with that. Radiant floor heating with it in locker rooms, under ice heating, snow melt around the building, in the seats, all kinds of things. And basically, you can eliminate the use of the cooling. You can certainly reduce the use of the cooling tower, unless you've got a big heating load. Probably can't get rid of it. You're probably going to need a fluid cooler or a cooling tower regardless. And a real simple way of done this on a number of smaller rinks. The simplest way of doing this is connecting the chillers, running the condenser to a ground loop, and then using heat pumps within the building or in other buildings nearby. Extract heat from the ground loop. They're going to run very, very efficiently. You've got a 60 or 70 or 80 ground loop in the middle of winter. Another way is to use the same heat pumps. You can just direct the flow of water, hot water, either to the building or to the ground loop. Or you can also take heat from the ground loop and put it into the building. Your mice is made. The problem with that is solved by the ground heat exchanger is that you can store energy when you don't need it, and you can pull energy from it when you aren't producing. Like an ice plant isn't always conveniently running when you want it to be, because the loads are going to be different on the ice rink than they are in the building. And again, the efficiency of the heat pump, you've got to be aware of what's happening with that. The COP changes the bigger the temperature lift is. So if you're heating the building with 80-degree water to a radiant floor heating system, that's going to be a lot more efficient than trying to heat that building with 110 or 120-degree air-going air handlers. This is the rink in Minnesota. They added a second rink to an existing building. Here's their existing rink. Here's the new rink that they added to it. This is one of those inflated buildings. If you've ever done the analysis on those, they need a lot of heat, because the only way they can keep a building like that up is pushing roughly 30,000 CFM of outside air, and when it's minus 30, that's a lot of heat. That's the only thing that keeps them inflated, keeps them up. So doing that, that's a good place to get rid of a pile of heat. And there's a bit of a connecting building to it. The building like that, that building is being heated. So looking at a double ice rink in a single soccer field house, peak heating loads are still 33% higher than the peak cooling loads. And the annual energy loads are still a lot higher than the annual energy heating loads. So what's going to happen then, even with 132,000 feet of drilling, we're going to get a temperature increase over time. So looking at a single sheet of ice versus and a soccer field house, loads are a lot closer together. Peak loads are still approximately equal, and peak cooling loads are approximately equal. You're still going to get this because your compressor heat is still going to go somewhere. But we've reduced the size of the ground loop by quite a bit. And then single sheet of ice with a double soccer field house, all of a sudden our heating loads are a lot higher, and our peak loads as well as the energy loads. Now we've got a bit of a balance. Gives you some idea of how much heating you can do, taking heat out of the ice. Yeah. Yeah. Not in Winnipeg. There's probably about 50 indoor hockey arenas, and probably about half a dozen or a dozen or so are open all summer. Most of them are shut down. Then you simply got to get rid of a lot more heat. Well, okay, if you're not making ice, for example, yeah, then the refrigeration load will be a lot smaller because you're not using the ice, you're not flooding it, and you don't have the radiant load on it as much or anything like that, so the refrigeration system isn't going to run as much. And then what you may have to do is looking at, if you've got a bigger heating load than that, than you are getting from the ice, then you may have to extract heat back out of the ground. Okay, so instead of taking heat from the ice and putting it directly in the building, you're taking energy that you dumped in last winter and pulling it back out. There's still going to be some refrigeration load even if the ice is covered, but not near as much. But yeah, you've got to take that kind of stuff into account for sure. Okay, one thing about once you've balanced the loads a bit more, what we found basically is that instead you can space the ground loops closer together. So in other words, instead of taking up more land area by spacing the boreholes, let's say 25 feet apart, you can reduce the spacing quite a bit, and without changing the amount of drilling that you need a whole bunch, because you're dumping energy in, you're pulling it back out. You're dumping it in, you're pulling it out. And the land area that you need, smaller. Balancing the energy loads to and from the ground is a fairly big deal. Doesn't matter how you do it, whether you melt snow with it or whether you heat a swimming pool with it, it doesn't matter what you do, but you can balance the loads one way or the other. That's going to benefit the system. It's going to work more efficiently over the long term, and the ground loop is going to be smaller, and you can take up less land area. So again, you can consider Ice Rink as an energy source for a district geothermal system. If you're in a colder climate, it's going to be difficult to use all the heat that you're getting out of an ice rink in Florida. That'd be really, really challenging. You couldn't find enough use for it. So basically, a refrigeration plant, ground heat exchangers basically provide storage, balancing the loads, reducing land area. Okay, thank you. Anyways, monitoring systems, I think the last part of the flow chart that I showed you was the operation of the system. And that I've come to realize is probably a fairly big deal. Oh, there we go. Again, this drawing basically, with the conventional system, you're working with basically infinite energy source. Long as there's gas lines out there, somebody engineer down at the far end of the line is making sure that you've got enough gas coming down the pipeline to heat the whole city of Albany or the whole city of New York or whatever. You don't have to worry about it as a designer. But again, with a ground source, you're designing that energy source. So with 8760 hourly energy model, you can get a reasonably good prediction of what the temperature should be throughout the year. And we talked about that a bit earlier, about you can get these kinds of numbers. If you got a decent energy model, you can get these kinds of numbers out of it. And if you put in hourly loads, you can get hourly predictions of what that ground loop should be doing based on a typical weather year. Some of the reasons that the temperatures would vary from that, there's a couple of reasons. One is the building energy model might be flawed to start with. Maybe you got a poor description from the architect or from the builder or from the owner, or the building is being used differently or occupied differently than you were told by the owner, or the way you described it in the energy model was wrong. And then the assumptions of the geology of the site, you may be wrong. You may not have realized that there was good water flow through that ground, or that thought there was ground water flow and there wasn't. So your assumptions may have been wrong. The weather data for the site is different than the data used for the model. And in mountainous areas, that can be fairly tricky. And then the mechanical system is being controlled differently than you've specified. So why is that important? Basically, what you're looking at is the efficiency of the heat pump changes as the temperature of the heat transfer fluid changes. And that happens both in heating and in cooling. The COP in cooling at 80 degrees Fahrenheit is almost 50% higher than the COP in heating at 100 degrees. So at 100 degrees, temperature difference, ground heat exchanger temperature. Ground heat exchanger temperature gets up to 100 degrees, the efficiency changes quite a bit. And keep it down at 80 degrees. Same thing in heating. Difference in the efficiency of the heat pump. And the compressor has to work a lot harder when the temperature difference is greater. In other words, if you've got a 50-degree temperature in heating versus a 30-degree temperature, compression ratio here gets up to about 6 versus about 4.5. That means the compressor has to work a lot harder. You've got to apply more energy to it. And the compressor isn't going to last as long, as everything's under a bit more stress. Same thing in cooling. Compression ratio, the higher the temperature, the higher the compression ratio, and the harder the compressor has to work. So As one example of a building, this is located in Winnipeg, about 42,000 square feet, horizontal directionally drilled borehole under the parking lot area. Distributed heat pump system throughout the building. And what happened on this particular building was that one mechanical engineering firm designed the distribution system and the heat pump system, and then another firm designed ground heat exchanger based on the loads. No one person was really completely in charge of that system. And then the system was designed with a gas boiler as an auxiliary heat source. So horizontal directional drilling, I think we've got about 72 horizontal boreholes that are about roughly just under 300 feet long and connected to the building. They've got a gas-powered or a gas-fired makeup air unit that supplies fresh air to the building. And it also pre-cools the building, or pre-cools the fresh air to the building. So the system was commissioned in May of 2010, and the temperature was slightly over 80 degrees by about the end of September, right around, right around here. And then gradually dropped a little bit and leveled out at about 60 degrees Fahrenheit. These are just a couple of anomalies in the system for some reason in the first season. But basically, one of the problems was that the controls contractor that was hired by the mechanical engineers that designed the building system had told them, this is a heat pump system. You know how those work, just put the controls in. So they assumed that because there was a gas boiler and they wanted the gas boiler to come on at 60 degrees like you would with a normal boiler cooling tower system, heat pump, as soon as the ground loop hits 60 degrees, you want the boiler on. So what happened is the system worked fine in heating. The system in the first year worked fine in cooling. And if we had caught this earlier, we'd have seen that it started out at 60 degrees. It should have caught that right there, instead of by the time we got over here. Here's what ground loop temperature probably should have been. So by the end of December, we were expecting to be around 50 degrees, give or take. And when I called them up just informally at the end of December, it was still over 60 degrees. So here is the highest point that they had. Here it hit 60, and here it's still 60. And you can see what happened to the air temperature. There's no reason that it should have been still 60. So what happened then was basically the gas boiler was decommissioned. Temperature dropped virtually immediately. Here's what the temperature should have been, and got pretty close to there. If this hadn't been caught, this wasn't the problem here. It probably wouldn't have been a problem till probably around here, the end of August, if maybe not the first year, but certainly the second year. Temperature would have gone up higher than it should have been. Look, probably like it would have been running at about all about 60 degrees, and then at this point here in the beginning of summer, there was enough heat coming from the building air conditioning that the boiler wouldn't come on, but temperature would stay up there. And then as soon as it dropped again, it would start climbing again, or the temperature would climb up. End of August, be up pretty high. So here's what was estimated that the temperature would have been if we hadn't caught it. So basically, it flattened out here, flattened out again, and each year probably get a little bit higher. And eventually, if not this year, eventually they would have to put a cooling tower in there to prevent the ground loop from overheating all the time. And that's no fault of the system. That's simply the way the system was being operated or controlled. So what happens then, the coefficient of performance, or the energy efficiency ratio in cooling, gets worse and worse. Starts deteriorating, and the system eventually, it would have probably cost them close to $100,000 to put a fluid cooler in at that point. So what happens then is the client thinks, well, why did we spend this extra $150,000 on the ground? Like, these things don't work, and we're not going to put it in our next building, and we're going to tell all the people that we know that these things don't work with the drug. So this kind of flattens out. Here, during the winter, the gas becomes the primary heat source. If we allow it to continue like that, this is going to heat fine. It's going to be a lot more expensive to operate, but it's going to heat fine. But compression ratio gets higher and higher. It's going to shorten the life of the compressors. And compressors are going to start failing in the second or third year probably. And interesting thing is that on this building, this was the warmest winter on record. This was the coldest winter on record. You can see that the temperatures here are a little bit higher than normal. Temperatures here are back down a bit. And then this year they got a little colder than normal. So what the building operator started doing is he's monitoring the temperature of the ground with himself. He's aware of how the system works now. And we spent a bit of time with him to help him understand how the ground loop is supposed to work and what he can do to control that ground loop temperature. And you can control the temperature of the ground loop to some extent. So basically what happens if the temperature is on target, here's what the heating BTUs, including the ventilation, and this is without the ventilation. So you've got this is basically provided by this difference is provided by the natural gas for the gas rooftop unit. These are the peak loads. So if the ground loop temperature is too high, here's what we were predicting they should be. And here's what the loads are. And here's if the temperature is too high, then they'll reduce the set point of the makeup air unit. In other words, instead of supplying 70-degree air or neutral air to the building, they may only supply 65-degree air to the building. So in other words, what that does is increase the heating load for the heat pumps. They have to now heat some of the makeup air because it's a little cooler coming in. So that basically what that does is extract more energy from the ground loop and cool it off a little bit more. So if it's too high in January, he lowers the set point on the makeup air unit. If it's too high, or if the temperature is too low in January, then what he'll do is basically bump up the temperature a couple degrees so that the heat pumps don't have to work quite as hard and won't extract quite as much energy from the ground. So you can control that to some extent. And since the makeup air is a fairly significant piece of the energy loads of a building, you've got a fair bit of control on that. So basically what the temperature has been, this was the warmest year, these are the average years, and this was last year, which was coldest. So there's roughly about a 10-degree difference in the temperatures from the coldest to the hottest year. It was designed to run at a maximum temperature of about 85 degrees. It got slightly above that on a couple peaks, and it got slightly below freezing on a couple peak cooling days. But generally, if the operator knows that this is about what the temperature should be, then they can do something if you build something in that they can use to control that temperature a bit. Whether it's a makeup air unit or a fluid cooler, it really doesn't matter. Or a gas boiler, really doesn't matter. But as long as there is some leeway and you can make these things work really well, very efficiently by managing the temperature of the ground heat exchanger and preventing it from continual climb up. So basically what we're looking at here is if they know that this is about what the temperature range should be, if it goes, let's say they're up here all of a sudden, or they're down here all of a sudden, then they know that there's an issue somewhere in the system. They should also know what the daily temperature range is going to be on a typical day. And with an hour-by-hour energy model that's plugged into a ground heat exchanger model that can do hourly loads, you can predict what that temperature should be on a typical day. in this case, it's just the building operator understands the system well enough. It's not that complicated a building, and he's doing it. There's a company out of Michigan that is automating this system. What they're doing is plugging the energy loads into the software that they've developed or have been provided by an engineering firm or whatever. Here's what the temperatures they expect it to be, and then they'll plug an energy meter onto the ground heat exchanger, and if it's off target, they'll run the fluid cooler or a boiler to compensate for that, or whatever they've got. It could be we've done one where we've integrated a horizontal ground loop with a vertical ground loop. We're using the horizontal portion of it to dissipate excess heat in the winter because it's very shallow, or we can absorb a lot of solar heat in the summertime when the ground is a bit warmer and dump that into the ground loop. But they've developed software that can see if the system is off target today and what the implications are going to be in 2 or 3 or 4 months, and try and get it back on target. And there are systems, I haven't seen any systems yet, but what they're talking about doing is being able to plug into a weather station. And if you can see that there's potentially a big heat wave coming in the next over the next couple of weeks, you can pre-cool that ground heat exchanger ahead of time, and it'll give it more room to absorb heat during that time period. Yes. Whatever you need, yeah. Like, the loop program. Yes, yes. And that's based on, like you're building, this temperature profile is a model built from an energy model. So we know what the hourly energy loads are. We've plugged in input the parameters of what the thermal conductivity is and what the diffusivity is and what the borehole configuration is and a whole bunch of things. And try and estimate what that temperature is going to be on an hour-by-hour basis. Yep. Yes. Yep. Mm-hmm. 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 Easily. Yep. 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 The peak load, the loads on the building change on an hour-by-hour basis, depending on what's happening. You could have a cooling load at 7 o'clock in the morning, where there's a few people in there. You might have a cooling load of 5 or 10 tons. 9 o'clock, a bunch of lights are on, computers are all on, a bunch more people are in there. You might be up to 30. 4 at 3 in the afternoon, you've got a whole bunch of people working away, and more lights are on, and it's got the sun beating in on the west facing glass, and the lights are all on, and okay, yeah. I'm not a big fan of it. Nope. Reason for that, one of the calculations for ground heat exchanger design, and I'm not the right person to ask what the math is behind those things. It's a tool for me. It's a hammer. And all I know is I can pick up that hammer and use it. I don't know how it works. But one of the things that it looks at is what the peak load is. You've got a big, let's say you're at 60, you've got it set back to 60 degrees at night, and you hit it in the morning, and all of a sudden you've got a huge heating load that's spiking up, and somehow you got to extract that energy from the ground. That ground loop temperature is going to go down like crazy. And in order to compensate for that, you've got that peak. If that load is going to be built, if you built that night setback into train trace, for example, it's going to show up in there, and you'll see that huge spike in there at 8 o'clock in the morning or 7 o'clock in the morning. And that's what's going to drive the size of that ground loop. And we've been looking at hourly energy models. What that tells you is the duration of those peak loads. If you've got monthly loads in there, I used to think that monthly loads are really, really great. Until you start doing modeling and start looking at what hourly loads can do for you, it tells you exactly how many hours that peak is going to last. But a monthly load tells you, the default in the software GLD, for example, is 3 hours. Is that peak load duration 3 hours? Or is it going to be 5 hours, or is it going to be 1 hour? Okay, so that's going to make a difference. That's why there are these more and more hourly energy models. Okay, so peak loads are a big deal, as well as how much energy you can shove into the ground at any time. I haven't got any experience with standing columns, personally. Starting to understand a bit more about how they work. I've never run into a geological formation where it made sense to try it. I can see how they work, because they're working in a couple of different ways. One is they're working like a borehole with zero borehole thermal resistance, so you're in direct contact with the ground. And if it gets too hot, then you can bleed off a little bit of water and you bring fresh energy into it immediately. So they work well. Yep. I've never done them. If I was asked to do one, I'd hesitate for sure, and I'd call a few people that I know that have done them, and I still might not want to do them. But that's just me. I've become a little bit more conservative over time. Yeah. Yeah, my thinking has evolved over the last couple of years that you can work with the energy loads on the building and deal with the building and manipulate those loads. You can do a heck of a lot with that much more cost effectively than you can put in more ground load. And I think it's going to, like, balancing the loads is a big deal in my mind, because it's going to make that ground loop last for forever, basically. Okay, and I got one more that might be worth taking a quick